All right, let's say that we've got a sequence. Let's let a sub n be a sequence. And again, remember, a sequence is a function. You could say f of n is equal to a sub n. Suppose that f of x exists for every real number. See, there's a big difference. Real numbers, do they only have to be whole numbers? No, real numbers could have decimals and fractions, right? So sometimes kids look at this and they'll say, what's the difference between f of x and f of n? N here is a whole number. You can only have whole number terms. You can only have your first term, your second term, your third term, your fourth term, and so on. Here they're saying, oh, now we're going to have f of x equals something. Well, x is a real number. That means that decimals and fractions are okay. What we're getting at, that big distinction is so critical right here, but it's an important one. We're really not even going to use it today. We're going to use it later on, you'll see. But we're going to say if the limit as x goes to infinity of f of x equals a limit, then so does just this ordinary sequence where n would just be whole numbers. N wouldn't be decimals or fractions. Now that's going to come into play later because we're going to go back to familiar calculus with x, and it hopefully will help out. Sometimes kids look at this and they'll say, wow, Mr. Dobner, I'm still having some trouble understanding what the difference is. It looks like semantics. It looks like word games to me. Here, maybe I can give you an example. Let's just say that I gave you f of n is equal to n squared, just for example. If you had that, you could say, well, I'm going to start at 1. I'm going to start at 1 right here. Actually, when I say whole numbers, we're not even going to have 0 coming into play. We'll just have the counting numbers. Whole numbers include 0. The counting numbers would be 1. You'd say, well, 1 squared's a 1. You plug in a 2. 2 squared's up here at 4. Can I connect these and make a nice looking parabola? No. This is a sequence. There is no 1.5 term. There's only a first term and a second term. By way of comparison, if I gave you f of x equal to x squared, you'd say, well, here's a 1 and here's a 2. Here's a 1. Up here's a 4. Guys, this is the parabola that we've known and worked with so much. It looks just like this. There are decimals and fractions everywhere. What this theorem is saying is, beautifully, if you need to resort to the math that you've done in the past with functions, and you can show that you arrive at a limit, then thank goodness the same will apply to just the sequence where you don't have a continuous connection. Like I said, that's not coming into play as much today, but it could help us out down the road. Likewise, we can also say as x goes to infinity, if f of x goes to plus or minus infinity, the same exact behavior would hold true for the sequence. Well, let's get into some real quick applications. Like I said, we have the choice of changing this for number 3 if we wanted to. If we really wanted to, we could say f of x equals 1 minus 1 over x. But right now, don't even worry about it. On the homework, you don't have to worry about it. It's an option if you so wanted it, but we won't even have to bother with it. They're going to say determine if this sequence right here converges or diverges. What you'll always do answering that question, guys, is essentially you're going to work out this limit. You're going to say as n goes to infinity, what happens to 1 minus 1 over n? Where are we headed? What is this 1 over n going to be going towards? 0. 1 minus 0 is 1. Yes, it converges to 1. Done. You take a look at number 4. You take a look at number 4 here and you'd say, well, wow, my goodness. Limit is n goes to infinity of negative 1 to the n. You wrestle with that for a second. What's that limit going towards? It doesn't exist. Yeah, it keeps bouncing around. I'm seeing a student show with his pencil. It's going up, it's going down. Why? What's happening? What's happening with the first term? Negative 1 to the 1 is negative 1. What's happening to the second term? It's 1. And the third term, you'd go to negative 1. We could graph this if we wanted to. And, in fact, I'd like to show you that graph, what it could look like. The first term's down here at negative 1. At 2, we're up here at positive 1. At 3, we're back here at negative 1. Going on forever. Now, let's just say someone says, I don't know, Mr. Dobner, I really believe infinity is an even number. And I am convinced that this thing's going to work out to a 1. Really? Well, I guess what I'm really getting at is, if you put a little bandwidth around positive 1, could you be guaranteed there'd be some term where you'd say, aha, once you get to the billionth term, you're never going to leave that bandwidth? No. You see, that's divergence. That's why I was showing you that bandwidth idea. As soon as you leave that bandwidth, that's divergence. Divergence does not mean that diverges, because that's really what they're asking. It is called divergence, but that's what it means to diverge. It means that you're not fitting within the bandwidth. You don't necessarily have to launch off towards an infinity or negative infinity. Okay? Number 5. Let's say I go limit as n goes to infinity of ln of n all over e to the 2n. Wow, this is reminiscent of something. You can look at this and say I'm getting infinity over infinity. Natural log of infinity would be heading towards infinity. L'Hopital, very good. Wow. So limits are going to show up with some regularity. L'Hopital's rule becomes our best friend. You'd say the derivative of natural log of n with respect to n, 1 over n. Down below, what do we get? Yeah, don't forget the chain rule, right? You take the derivative of the inside, you get it 2. And guys, right now, if we just clean this up, I hope you can see that we really get 1 over 2n e to the 2n. Why? Because when you're dividing by something, it's the same thing as multiplying by its reciprocal. Divide by any number. Like if you say, I'm going to divide a number by 5, it's the same thing as multiplying by 1/5. That's what we're seeing right here. Now what? Where are we heading with this thing? Down below, infinity and another infinity multiplied together. 1 over infinity is going to 0. Yeah, it converges. Converges to 0. Okay? So, I'm going to put some stars right here. Oh, is this important? We're going to use and reference this theorem repeatedly. We're going to do that over and over and over again. The limit is n goes to infinity of r to the n goes to 0 if the absolute value of r is less than 1. And yeah, I heard someone say it makes sense. I hope it does. Look, the sandwich idea. That means when r is between 1 and negative 1, when the base of this exponent is between 1 and negative 1, you're going to head towards 0. Let me give you an example, just real quickly. Let's pick a number between negative 1 and 1. How about just something real basic like a half? If I took 1/2 squared, don't we get 1/4? What about 1/2 to the 5th? That becomes 1 over 32. 1/2 to the 10th. The denominator is getting bigger and bigger and bigger, isn't it? Where's that thing headed? 0. The same thing would happen with negative 1/2. If you took negative 1/2 and if you were raising it up, what you're seeing is that thing's going to 0. By way of comparison, what you're going to see is if r in absolute value is greater than 1, that means r is greater than 1 or r is less than negative 1. Right? That's the great or situation. Great or. You'd have r greater than 1 or r is less than negative 1. That's the alternative. What we're going to see is, imagine that you're taking 2 to the n or 5 to the n. You'd say, wow, that's going to grow pretty fast, isn't it? Yeah, you're going to be heading towards infinity. What if I took negative 5 to the n? You could say you're going to bounce between positive and negative values. But if you put absolute value around there, you're going to be going towards infinity. This diverges. As soon as the base is bigger than 1 or smaller than negative 1, that means you have divergence. Okay? So let's take a look right here and see what's going on. Number 6, they just want us to list the first 4 terms for 6a. So negative 3/2 to the 1, you'd say, well, that's negative 3/2. Here I've got negative 3/2 to the 2. That's going to be 9/4. A sub 3, you get negative 3/2 to the 3rd. You get negative 27 all over 8. A sub 4, you'll have negative 3 to the 4th. Wow, that's 81. 2 to the 4th is 16. So yes, you are alternating between positive and negative values. But look at those fractions. Ignoring the plus or minus signs in front, the fractions are getting what? Bigger or smaller? Bigger. 80 divided by 16 is 5. This isn't even 4 yet. So you're getting larger as time goes on. Why? Because what's your r here? R is negative 3/2. The absolute value of r is bigger than 1. This diverges. If your r is bigger than 1 in absolute value, you will diverge. By way of comparison, you come over here, a sub 1, well, negative 1/10 to the 1. Say, hey, that's negative 1/10. A sub 2, negative 1/10 squared. Say, well, that's 1 over 100. A sub 3, you get negative 1/10 cubed. Well, it's back to being a negative. But you'll have 1 over 1,000. And you get the idea. Raising up to an even power, you get something positive. I'm going to have 4 zeros down here. That's 1 over 10,000. And looking at that fraction, ignoring the negative sign, you're getting smaller. That denominator keeps getting bigger. What's your r here? Your r is negative 1/10. Your absolute value of r is less than 1. You converge. It converges to 0. Even though you're bouncing between positives and negatives, you're getting so small over time that you just get closer and closer to that value of 0. You could put a bandwidth around it and see what's going on. In closing, the last page really is just a reference. It says, a sequence is monotonic if successive terms are non-decreasing. Non-decreasing means it's increasing or doesn't change. Right? That's what non-decreasing means. It just means that you don't decrease. That means that either you increase or stay the same. Or non-increasing. Non-increasing means that you're decreasing or don't change. Your derivative would be non-negative or non-positive. And A sequence is bounded if you're always